is now the day after filming. My friend who has been helping me out has gone home, and for that reason the quality of the video has probably dropped off. It takes about 10 times longer to film a job that you're doing than it does to just do it. It only really takes about 2 hours to change those control arms, but by the time you line up all the different shots, it can take a lot longer. I know it's a very small crowd of people doing DIY work on their Maseratis, but hopefully the few of you that are out there enjoy the video, and I will keep making them as I go along. But this is the bit that I really find interesting personally. I want to discuss how these original arms were designed and manufactured, the problems that it's caused, and the decisions behind why I resolved it the way that I did. Let's start with the main issue that these arms have, which is this ball joint here. Having a look at this ball joint, it doesn't look particularly unusual, but when you have a look at a cutaway of the arm, you'll see here that we have this other rather unusual cutout. This here is a cup, which would sit in here, and the reason it would sit like that is because the ball joint uses the arm itself as the seat. This was then press fit into the arm, and this little piece of metal was pinned across the top of it so that it would maintain its position. This introduces a few problems. The most obvious is that if this ball joint fails, the arm is scrap, since it is integral to the arm. It is the arm. The second is the cause of failure. Most people will tell you that you need to get these rubbers inspected since they're the cause of failure, but they have nothing to do with it. Sure, if these fail, the arms will fail sooner, but these arms will fail regardless, and they will always fail premature to a conventional ball joint because of the way that they're arranged. Conventional ball joints are typically arranged in compression or tension, but these arms are arranged in compression and tension. Every time the car accelerates or presses the brakes, this ball joint will load up in both directions. The problem is that you can only design the ball joint to be rigid in one direction. As you can see that this is press fit, what that means is that once this joint is in tension, it has the chance to pull this ball joint even a fraction of a millimeter out. Once that's done, there will be play that can never be rectified. Press fitting into aluminium is a difficult thing to do from a design and engineering point of view, that is. Technically it's easy to just press something in, but the problem is that the rules for press fitting are actually really complicated. You have to destructively test it if you're ever doing a unique application to know that it's even safe. So combine that with the fact that aluminium has some rather unique wear properties which prevent it from maintaining its rigidity over its entire life. What's most likely happening is that just over several cycles, these are pulling forward a fraction of a millimeter, introducing play that can never be fixed. So that's why these ball joints are a big deal. Once they're gone, they're gone. Moving further on to the body of the control arm. I sent a sample of this material out to a lab, and it is a grade of aluminium called 4000 series. I can't remember the exact grade, but it'll be on the screen as well as the full material readout. One of the interesting things about that material result is that a lot of people assumed that these were forged. There's no evidence at all of any surface hardening features, which indicates that these are in fact a casting. Judging by the quality, they're probably a die cast, but it doesn't really matter. What that means is that there is a casting seam along the body, and this becomes a focal point for stresses since there is no tension in the surface to try and maintain this seam. That becomes relevant when we get to the bushings. Another thing to keep in mind is there are two versions of this control arm. This is the later model, which is heavily reinforced. There's no cutout here in the center section, which you can see in the older arm to reduce weight, and more importantly, there is no reinforcement around these bushings on the older version. A good thing to know is that manufacturers, OEMs in particular, will not change a design unless they have to, because it's a very expensive exercise. So that tells you that Maserati knew that there was a defective by design issue with these control arms. So let's look at these bushings and assess the problem there. You can see here the casting seam. Now, though the casting seam is obvious on the outside, that casting seam is continuous through the entire body. It'll be on the inside where it's machined. It may not be visible, but there will be a seam in the crystalline structure of the metal. When you press the bushings in, they are press fit and they provide tension outwards. Combine that with many cycles and bumps and the fact that aluminium has the properties, unusual properties with its endurance limit. What this means is that you end up with a situation where a fatigue crack can propagate through the material, through to the thinnest point, which is effectively here. Even on these reinforced arms, they do have a tendency to form cracks here. On the older arms, they're known to just spontaneously fail from cracking. Now, the reason for that is multiple. The lower arms do all of the heavy lifting, not the upper arms, and I've got some results that can show that in a bit. But I just want to show why they fracture along that seam. So what I've got here is a force applied outwards from inside the control arm. It's only a small force, and definitely nothing close to the limit for this material. And what I've gone and introduced here is an imperfection in the surface. That's a 0.5 millimeter deep imperfection, and it's only on the surface. Now, the reason it's like that is just to show that the stress can focus. So you should all be able to quite clearly see that there is a focal point for the stress. And again, this is well and truly below the limit of this material. This is just for illustrative purposes. But what you should take away from this is that on that casting seam, there will be imperfections in the crystalline structure because of the casting process. And with a force applied outwards, that will change and cycle from temperatures as well as the arms moving up and down. There will be a focal point for all of that force into this center point here. So every time you try and rebuild these arms, you're going to have to push out the old bushings and push new ones in, and that will be a high stress cycle, and that will increase the chance of fatigue. So that matches the experience people have had when they've tried to replace the bushings, that they'll often crack during that process. And if they don't, then I think you're really just running the risk of them cracking while they're on your car. And that was a reason why I didn't think the OEM arms were suitable for rebuilding and were only suitable for replacement, is that the evidence is there from the real world that they do fail along this point here. The bushings aren't actually bushings, though I've been referring to them as bushings. They're what's called a flanbloc. This is a cutaway of one. I've literally just cut it in half in place. You can see the control arm here. You can see a metal sleeve, a rubber layer, and then 2 inner metal sleeves. Now, this is seized in place from corrosion, but when these are new, this can actually rotate freely. There's another disc on the other side. So it's effectively a bearing with a rubber isolator. So these 2 inner sleeves rotate freely against each other, and the rubber isolator helps with a bit of NVH. The reason that this is done is it gives you a good middle ground between a bearing in your control arms, which have very harsh NVH and they don't have a very long life expectancy because of the direct contact that they have, compared to rubber, which can absorb some degree of vibration. But you can see quite clearly there's not a lot of rubber in there, so you would be getting quite a lot of vibration and force into these control arms. With all of these things in mind, I originally considered rebuilding these. The first problem that I had with rebuilding these starts at the ball joint. These are the ball joints that I used, and these ones are threaded body. Firstly, you can't use a steel threaded body into an aluminium threaded body. The material properties to do with the endurance limit effectively mean that you can really only tighten it 2 or 3 times and then it'll start pulling out pieces of metal. If you've ever worked on an aluminium block on an engine and you pull out some studs, a little piece of metal will always come with them. That's why. It's a material property of aluminium. It's completely irrelevant what grade of aluminium it is, it will happen. So if I wanted to rebuild these and cut a thread into it, I might be able to do this a couple of times, then the arms will be completely trash anyway, at best. Then, if you have a look at the depth that this goes into, if I removed the threads and tried to press fit it, I would be left with very little material on this, and the FEA confirmed that there would be substantial amounts of stress in this area here. I'd be quite concerned about fractures around a press fit here. More than that, press fitting is a very imprecise science. You can't calculate it out from first principles reliably. Anything that you press fit, you are supposed to do destructive testing in batches to make sure that it's behaving the way that you expect. There should be some screenshots from the SKF installation and sort of selection manual up on the screen just to give you an idea of how complex it is, and that's when they've already done the research and they're providing you guidance on steels. But going steel into aluminium, they have different rates of thermal expansion. The short version is it becomes very dangerous very quickly to do a press fit on something like this without doing the correct analysis. So just on this piece alone, I wouldn't have been able to proceed with a safe rebuild of these arms. Moving back here, because these are prone to failure just with the standard bushings as they are, while they're in the car, this is just not a safe thing to rebuild. I've heard of people trying to replace these bushings, and during that process they've split these arms. There's really no point trying. It's just going to be a waste of time, and if I do succeed, it's very likely that there's going to be hidden or invisible cracks in here, and then there's going to be very high risk of fatigue cracking up in the ball joint as well. It just wasn't a safe way to proceed, and that's why I decided to make my own arms from scratch. So let's have a look at what I did with those. We'll start at the opposite end and work our way up to the ball joint. For the bushings, I recommend using OEM bushings, or flanblocs, as I should say, or urethane bushings, since urethane won't swell quite the same way that rubber bushings do. These parts are made from billet, so they do not have a casting seam, and as you can see, they're further reinforced even compared to the late model arms. Since they're made out of a single piece, it's actually cheaper in terms of manufacturing time to just do a single pass like that instead of to use less material. Since I'm removing material to manufacture this, whereas the OEM arms are adding material, they were trying to save money by making a smaller casting. In this case, it allows me to make these more reinforced effectively with no cost penalty compared to making them a direct copy. With this thicker material here, and no point for fatigue to form, using the correct bushings, these will be serviceable for a much longer period of time. Another difference with these arms is the concerns of the mechanic. The bushings in this case insert from this side and can be easily pulled through using a bolt, which is shown in the assembly video. This allows these bushings to be pushed out easily at a later date when this arm is intended to be rebuilt. Not something that is easy to do with the OEM arms. You need special tooling to reach to be able to push the bushing from the inside, whereas you can just sit this on a press and push it from both sides without any trouble. Moving into the material, this is 6061 T6 aluminium, or a 6000 series aluminium. This is a much stronger material. There should be some data on the screen now showing you a comparison between the 4000 series that the OEM arm is and the 6000 series that this was manufactured from. What this means is that I could technically make these substantially lighter than the OEM arms and still exceed their strength. However, I've chosen not to do that. At the completion of the FEA, I have instead decided to focus on making these substantially stronger than the OEM arms, which is also why this little raised section is here. The FEA showed this as a point where stress was building up, so I decided to introduce that as another reinforcement. These arms have a calculated factor of safety of 20. What that effectively means is that the expected stresses that these are to see these can see approximately 20 times that stress level.
The final step in making sure that these arms were safe to implement was to contact an automotive engineer in Australia and get their advice on making sure that these control arms met the Australian design rules. Now, the Australian design rules are for modified vehicles, and these arms are OEM replacements, so they don't technically need to meet those guidelines, as they're substantially more stringent and onerous than what would have been put on the OEM. However, I thought it would be good to compare them to the ADRs, which should be up on the screen now, and these results were sent off to an engineer using an analog model of the upper and lower control arms, so the whole assembly, and these were put under incredibly excessive loads up to 20 kilonewtons in some directions and 50 kilonewtons in others. So in these scenarios, the lower arm is doing almost all of the heavy lifting. You can quite clearly see it's the only element that's experiencing any real stress. However, in all cases, the factor of safety exceeds 20 in this real world analysis.
Since they're aluminium, they will eventually fail, but that should be well outside of the lifetime of the vehicle, or at least my lifetime, so that I'll be long dead before it becomes a problem. The insert for the toe adjustment here is made out of 316 stainless steel. This is to assist with corrosion, preventing this from being adjustable in the future. Combined with anti-seize, these should have a much longer life expectancy than the original parts. Moving forward to the ball joint. As I said previously, I cannot reasonably reuse this area if I thread a steel-bodied ball into an aluminium receptacle. So as discussed in the assembly video, I use a steel sleeve, which is permanently affixed into the arm, which allows me to repeatedly remove and install ball joints. Anticipating the placement of these ball joints due to the nature of failure, this seemed like the best option to maintain the serviceability of these arms into the future. And as shown in the install video, these studs have been manufactured as part of the arm to make them more serviceable than the OEM component, simply because they have a stud on them, have a hex on them for a socket, so that they can be easily removed when the arm needs to be removed. For comparison, this is one of the OEM toe adjusters. I wasn't able to remove the stud. This is the one from the installation video, so I needed to use a stuck bolt extractor, effectively destroying the stud as part of its removal.
What we're looking at here is a factor of safety plot from 0 to 20. If it's blue, it's 20 times the load that I specified. Now, that load was just arbitrary. It was picked not because of any relationship with the vehicle. It was just as a method of setting a benchmark for the performance of the original arm. Using that, I was also able to view where stresses were building up within the arms, and you can see that there's a point across the longest section where there is a relatively high stress, or rather a high stress focus. Moving on to the arms that I've built. Using the same scale, you can see that this arm is experiencing very little stress. In the same factor of safety plot with the same loads, this model is well and truly capable of meeting or exceeding the performance of the original arm. If I look at stress, you can see that there is lower degrees of stress through this arm and that it is more evenly distributed. One of the ways that I was able to achieve that was just making this section here slightly thicker, following on from the results of the original arm.
Hopefully that answers most of your questions, and hopefully this has been edited with some nice pictures, not just me talking blandly over some bits of metal on my desk, and I hope this helps solve a lot of the problems you have in the future.